Hello everyone, today I'm going to do the two other topics, which is topic 5 and topic 6. I'll leave topic 4 and topic 9 to the very last, saving the best for the last. So topic 5 will be on electric field for 5.1, magnetic field for 5.4, and then 5.2 and 5.3 will be the circuit rules. As usual, for the previous video, I will not focus on everything because by now you should know the facts. I'll focus on important ideas, concepts, and areas where students tend to have issues with for those topics I mentioned. So let's start off with 5.1. So 5.1 covers electric field. Now, for electric field, you have to know that it is very important for you to know that the electric field strength, E, the symbol E, it is equals to KQ upon R square. Usually formulas is not the issue. If there's any issue is with the understanding that R is measured from the center of charge to the center of charge. This you have to be careful of. But as a side point, if you place two conductors which are positively charged, you need to be aware that the positive charges may actually repel, not may actually, they will repel each other, and some of the charges will reside over here. So the center of charge, it will be actually bigger than the distance between the center of charges will be bigger than the center of the spheres. So this you have to be aware. But most of the time we assume that the center of the charges is the center of the sphere itself. So anyway, just be careful that R is the center, the distance between center of charge to center of charge. Now what I'm more careful with and what I'm more concerned with is that the students must remember that the definition of electric field strength is the force per unit positive point charge. The point charge and positive are the terms that students tend to miss out on. And the reason why this is important is because it is not true if it is not a point charge anymore, and it is positive because it's by definition. And why is this important? Because this is the reason why in secondary school you learn that for positive charge, the field strength points, the field points outwards. Why? Because by definition it is positive. So if I place a positive charge over here, it will experience a force this way, and therefore the field is pointing towards the right over there. And that's why for negative charge, if you place a positive dash charge, the force points inwards, and that's why for negative charge the field points inwards. So this is really the defining idea that governs how the language that we use in the drawing the field lines. So very important definition. Now, next thing you need to know is that because it is a force, because it is a force, it is a vector quantity, and that's what sets it different from gravitational field, where it is only attractive. So for electric field, if I have positive, there will be a point where the field cancels off, somewhere in the middle depending on the charge. But if I were to have a positive negative, then say if I want you to find a point where the field strength is equals to 0, and this is 2Q, this is minus Q, then in the center, the field over here due to this one is pointing here. The field over here due to this one is also pointing here. So they don't cancel. Now the point where it cancels will be either here or here. So the question is, where is it going to be? Is it here or there? Now do remember, as a rule of thumb, is that the point where the field is equals to 0 is always nearer to the smaller charge. So the smaller magnitude of charge. So it will be somewhere here. Because if it is nearer to the bigger charge over here, then it is impossible for the field due to this smaller charge to cancel away the field due to the bigger charge. Alright, so because it is a vector quantity, that's why we talk about direction. Very important idea that electric field strength is a vector. Likewise for force. Now the next thing I want to go into is this idea about potential energy. Now it is in your syllabus for 5.1 to know that potential energy, or the change in potential energy, when a charge is moved through a potential difference. Now why is it important? Because it's linked to the next point, which is in electric field, which is in 5.2, in an electrical circuit, your W is equals to QV. And this is actually the definition of your potential difference. The definition of potential difference is the work done to drive a unit charge between 2 points. Now this is not only applicable for electrical circuits, it is applicable for any circuits. If I drive an electron over a potential difference of 5 volts, then the potential energy change will be the charge of electron times 5 volts. So it is from here, that's why we derive this one, the definition of potential difference. Now you also need to know the difference between potential difference and EMF. Now EMF, you talk about sources. Potential difference, you talk about devices. So EMF, you always talk about the other forms of energy converted to electrical per unit charge driven through the entire circuit. Whereas for potential difference, you always talk about electrical energy converted to other forms of energy per unit charge driven across 2 points. Now 2 points need not be the whole circuit, can be the whole circuit. So that's why sum of potential difference is equals to the EMF. So you need to be very clear in summary of the difference between potential difference and EMF in the context of circuit. We are already moving into 5.2 if you're unaware. So 5.2, you need to know some of the basic equations. Basic equations. V equals to IR. You need to know V equals to W upon Q. You need to know power equals to I squared R equals to V squared upon R equals to VI. You also need to know that R is equals to rho L upon A. You need to know Ohm's law. You need to know how to draw the IV graph for the ohmic conductor, for a bulb, and also for a thermistor. Alright, so these are basic stuff that you need to know. What I'm more interested in is whether you know how to use this equation. That's for still within 5.2. Now, the way you go about using this equation is that, let me draw some interesting examples. Say for example, if I were to have bulb A and bulb B, and bulb A resistance is 4 ohm, this is 2 ohms. Which bulb will be brighter? So how do you know which one is brighter? You look at power. Now there are 3 equations for power, so which one do you choose? I would choose I squared R in this circuit, in this configuration, because why? It is a series circuit, so you need to know that the current are the same. And because the current are the same, I need to choose an equation that allows me comparison of the power with only the resistance. That's why I chose this one. So in this case, since the current are the same, therefore the bulb A will be the brighter one. However, if I were to choose a circuit that looks like this, now it is parallel. Still 4A, 4 ohm, and B 2 ohms. Which one will be brighter? Now I can't choose I because the I will be different for each of them. So I choose V squared upon R because V are the same. And that's why for this circuit, on the right hand side, the bulb A will be the dimmer one because it has a larger resistance. So what am I trying to say? You need to use the equations based on what you're given, especially for power, whether it's series or parallel. For comparison, I would say that most of the time you have to use I squared R in the series circuit, and parallel circuit V squared upon R. Now, next thing. Kirchoff's law is the next thing that I want to go through. Oh yeah, one more thing before I go to Kirchoff's law is that whenever you use reminder, V equals to IR, the V of the thing, I of the thing, R of the thing must be the same. What am I trying to say over here? Illustrate using example. So this is say 4 ohm, this is 6 ohm, this is 9 ohms, this is 2M. Now if I ask you to find the potential difference across 4 ohm, you take V equals to IR, which is equals to 2M times 4, which is equals to, if this is 8, which is equals to 8 volts. Now you do not find V, let's say this is B, this is C, you do not find VB by taking 2 times, this is IR, 2 times 6. Why? Because this is not the current, this is not the current, which is 2N, it's not the current through the 6 ohm. It splits up. So how do you find the potential difference or the current through the 6 ohm? Now you need to know the PD across here. Remember, if you want to find the I of B, you need to know the R of B which you have and the V of B. So how do you find the V of B? Now that's when you use series circuit laws. You know that the PD is, oh I forgot to give, this is 18 volts, say for example. If this is 18 volts, this is 8 volts, then the PD across, this is wrong by the way, PD of V will be equals to 18 volts minus 8, which is 10 volts. Then you take VB equals to 10 divided by 6, which is 1.67 volts, M. No, there's something wrong. 10 divided by, no, I want to find current. Current will be equals to 10 divided by 6, which is 1.67 M. So what am I trying to say over here? That whenever you use a circuit, you can use this very important idea that whenever you use V equals to IR, you need to make sure that the V of, I of, R of are the same. And this is a very important habit in using every equation. You need to be very clear, crystal clear, of which quantity are you plugging inside there. Is it the same quantity? Alright? Now the Kirchoff's law is actually very simple. In your syllabus, very clear cut. 3 currents usually. And revision, Kirchoff's first law, basically I equals to I1 plus I2. Whatever current flowing in equals to whatever current flowing out. The other one is summation of V equals to summation of EMF. equals to summation of IR. Now let me give you one example. To make your life a little bit more interesting, I've reversed this one. So this is 10 volts, 15 volts, say 20 volts. And this will be 5 ohm, 10 ohm, 15 ohm. Let's assign the current I1, I2 and I3. So in this way, I3 plus I1 equals to I2. So I3 plus I1 equals to I2. And then let's consider the loops. So let's consider this loop and let's take this as the positive direction. Remember, the directional EMF is always from the lower to the higher. So this direction is positive, so 10 is positive, plus this is positive but it's pointing here, so it's minus 15, equals to the summation of IR. The current I3 is flowing this way and this is the positive direction, so therefore it's 5 times I3 plus this direction is positive but the current is flowing here for I1, so it's minus 10 I1. Therefore the circuit will become, the equation will become minus 5 equals to 5 I3 minus 10 I1. Let's take a look at this circuit. Let's take this to be the positive direction. Now for this equation over here, this was positive 15 because this is the positive direction, and plus this is also the positive direction because it's pointing this way, so it's plus 20. This is the positive direction, so the current is pointing here, therefore it's 10 I1 plus the current is flowing this way, so it's plus 15 I2. So therefore this equation will become, so you got 3 equations, 3 unknowns, you'll be able to solve for the answer. Alright, in case you can't see, just in case you can't see, I'll just switch this over here a bit, freeze it there for a while, and now I'm going to turn this back. Alright, so this is Kirchoff's law and the use of the typical circuit equations that you need to know. Next thing, 5.3, you need to know internal resistance. That's the key of 5.3. There are other peripheral ideas, but the key of 5.3 is internal resistance. And for internal resistance, you need to know that in normal discharging curve, discharging situation, you have this E and this is small r, this is big R, and this is I. So in this case, you have E minus IR equals to V terminal. You need to know that in operating condition where there's a current flowing, there will be a V that's lower than E. Alright, because it's a minus IR. And the only case where you have the E measured is where you have no current flowing. That means you connect the battery directly to a voltmeter. Now another equation can be given or can be used, which is this equals to VT as well. Basically you're trying to find a PD across here, which is R divided by R plus R times E. So these are 2 equations that will be very useful. From this equation, you need to know how to sketch VT versus I. With this graph, this is your E and the gradient is equals to minus R. This is one of the ways, in fact, to find the internal resistance. You put an ammeter over here, you connect the voltmeter over here, and you need to know the setup. And this is the way, by varying the variable resistor over here, you can get different values of VT and I, and from there you can find the internal resistance. Alright, so this is 5.3. 5.4 is the main thing is magnetic field. I will leave the part on using the right hand rule, you know, the current in a wire, that you have to go and look out in the notes. What I'm more concerned with for 5.4 is the use of the equation BIL sine theta and F equals to BQV sine theta. You have to know that this angle theta over here must be very clear that it is the angle between the current and the field, and this is the angle between the velocity and the field. Must be very clear about that. So because questions will give you, say for example, a velocity, a particle move like this, the field goes like, say for example, this, and I give you this angle over here, 60 degrees. So what you should plug into the equation is 30 degrees. Do not plug in any angle that you see in the question. Must be very clear. Go back to the definition, check, because once you make the careless mistake, you will not find it. Very difficult for you to find it. Other things like definition of 1 Tesla, check it out in your notes, it's inside there. How do you define the magnetic field strength and how do you define 1 Tesla? Lastly, for 5, you need to know this thing called velocity selector, which is when you place a cross field situation. So in this case, you have a positive plate, negative plate. Say for example, you got a negative charge going through. The negative charge will experience a electric force upwards. Now I can apply a magnetic field so that it experiences an equal and opposite force due to magnetic field downwards. How? So negative charge, so current here. Field force must be downwards. So if I apply a field into the page, the negative charge will experience a force downwards. Now you should know that if FB equals to FE, the charged particle will move right through without any motion, without any deflection. Now this will happen when BQV equals to QE, Q cancels off, V equals to E upon B. Now when this happens, the particle just goes right through without any deflection. So this is what we call a velocity selector, because only particles with this velocity will pass right through. So what can you be asked? Given the E and B, you need to know how to find V, or given any other two quantities, you need to find the rest, the last one. Next one, you can be asked to identify, given the magnetic field, identify which one is positive, which one is negative. So by identifying the forces, you'll be able to identify which one is positive, which one is negative. Reverse, I give you the positive, negative, I want you to identify the direction of the field so that the particle can pass right through. Lastly, if I were to have a particle with velocity bigger than this, in this case, how would the particle be deflected? Look at the forces. Which one depends on speed? This one, FB. So if I have a particle with velocity bigger than this velocity, the magnetic force will be bigger, so it will go down. Therefore, if I have a particle with velocity smaller than this value, the electric force will be bigger, so it will be going up. So this is how you determine which direction you will go if it is not the V equals to E upon B. And that's it for topic 5. Not sure whether I'm making it sound too easy, but these are some of the important things you need to know. So topic 6 is basically about gravitation and circular motion. You need to know that for gravitation, the formula F equals to gmm upon r square, and G equals to force upon m equals to gm upon r square. Same thing. The R is determined from the center of mass to the center of mass. Now be very careful that the center of mass may not mean the geometrical center, because we are assuming that the density of the object is uniform. Say for example, if I got a weird planet where this half is more dense than this half, then the center of mass will be here. So it is usually assumed that it's uniform, which is a fair assumption, but be aware that center of mass, not center of the sphere. Alright, but most of the time it is. So that awareness is important. So the thing is, you also need to know that G equals to F upon m. It is the force per unit mass on a point mass. So the point mass is still there. The previous one was point charge, but of course you don't have a positive mass, so it's just force per unit mass on a point mass for this one. Now for G over here, it has a special meaning. This is also the acceleration of free fall. So when the question asks you or tells you that the acceleration of free fall is 9.81, it is also the gravitational field strength, which is 9.81 Newton per kg. Newton per kg. So you need to know that the field strength is numerically equals to the acceleration of free fall at that point. I went through for electric field. If you got two masses, since gravitational field is a vector quantity, is force related, there is a point over here where the field is equals to the field, and this is the neutral point where the G resultant is equals to 0. Alright, so you need to know, the examples are in your notes, you need to know how to find the position of that point. So this is more or less for gravitational field, forces related quantities, forces related questions. For the next one, which is 6.2, you need to know circular motion. Now, two very important axioms that I always remind my students about for circular motion is that Fc is a net force to Fc points to center of circle. Let me use two examples to illustrate this further. I think I've used this before, but I'm going to say this again because it's so important. Now, if I got an object going through a conical pendulum, it goes like this. It doesn't go like this. This is the uniform. This is the usual pendulum. It goes, scratches the circle. So it's a conical pendulum. If I were to ask you to draw the free body diagram, it has to be only T and W. You cannot add the centripetal force into a free body diagram. You must never ever, because centripetal force is a net. Centripetal force is a net force. Just like if I tell you that in a box, a 5 Newton force acts towards the right, a 3 Newton force acts towards the left, you will never draw this. 5 Newton to force to the right, 3 Newton force to the left, you're not going to draw this. Right? So you don't draw the net force in the free body diagram. This is wrong. So likewise for this one, you do not draw the net force into the free body diagram. However, if I were to sum up this force and this force, this will be the resultant force, which is the centripetal force. Okay, so the other one, very popular example, you got an object spun around, what am I doing? Spun about a center over here, so it's swinging over here. At this point, tension and weight acts in this direction. This point, tension and weight acts in this direction. So we know that centripetal force is the net force. So centripetal force at the bottom is equals to tension minus W. Why not weight minus W? Why tension minus W? Because the net force points here. So I take T minus W. T plus W equals to mv squared upon r. Why do I write it this way? Because the net force is the centripetal force, and they point towards the center of the circle. So it is very important for you to remember this too. The rest of the equation is really just peripheral. I mean, you need to know the equation F equals to mr omega square, F equals to mv squared upon r, V equals to r omega. One last thing that you need to know is this thing at this point. You need to know that at this point there is a point. There's a velocity where the object can go, the string can go loosed. Say for example, for this equation, it is possible for my weight to go to 0, for my tension to go to 0. At that point, mg will be equals to mv squared upon r, and your v is equals to root rg. You need to know how to prove this. You need to know how to use this if the question requires you to use. Now the signal for you to use this is statements like find the velocity at which the string goes loose. Find the velocity at which the object loses contact with the ground on the top. Find the minimum speed to complete circular motion. So these phrases point to this minimum speed over here. Alright? And occasions also requires you to apply conservation energy from here to here. So if the object were to complete the circle safely, you must have this speed at the top. So what's the speed at the bottom? Then you use conservation of energy. mgh plus half mu squared equals to half mv squared over here. Alright, so that's more or less it for the topic 5 and 6. The next lesson I will upload will be on the one on topic 4 and then topic 9. I'll do it separately because I'll bring 9.1 to 4.1, but the rest I'll do it separately because it's a big topic. So I'll do 4.1 to 4.5 plus 9.1 for 4.1 together with 4.1, and then I'll do 9.2 to 9.5 separately. Alright, I hope this helps you bring back some memory, some memories of the important points that you need to know in preparation for the exams. Alright, thank you.